Okay, so first of all, before I begin, can I just see a show of hands? Who's actually heard of Arm? Okay, I don't see any hands. So basically, I just need to get used to this audio. Basically, Arm is a CPU architectural design company. Arm designs the chip architecture that goes into most phones, as well as most of the embedded devices that you guys will use. For example, things like this will have a little microcontroller inside them, and those will most likely be powered by an Arm-based CPU. Has anybody here heard of Raspberry Pi? Okay, yes. So Raspberry Pi makes use of an ARM-based CPU. Arduino. Okay. Also, most cell phones are using ARM CPU. So, like your Samsung phones and your some of your MediaTek-based phones as well are all using ARM. So ARM has been around for about 40 years, more give or take. And ARM has a legacy, a rich legacy in designing low-power, energy-efficient CPUs. So the idea behind mobile phones has been to have energy efficiency and maximum performance. So that's why ARM's rich legacy in the mobile phone space for the last 10 to 15 years has given ARM an edge in terms of how CPUs can be made to run using less power. That's important, obviously, in the age of sustainability and energy efficiency. And also, your computational performance is also better than CISC. Does anybody here know what RISC or CISC instruction sets are? Some of you might have heard of that if you do computer science. So essentially, ARM is a RISC architecture, was a RISC architecture from the beginning. And that gives the benefits of better throughput computationally as well as lower energy usage. So now what's happened is we're in a world of AI and an AI revolution where we're moving AI from the cloud down to the edge. So most of you guys saw when ChatGPT launched a few years ago, when you made use of it, you had to obviously have an internet connection. You're calling a backend. Most of you guys who started building with apps around ChatGPT had to call APIs. So when that API goes down or your internet connection goes down, you have no choice but to wait for it to come back up again. The future that we're going to aim towards is bringing those models from the cloud down to the edge to run locally on your devices. So an edge device, the definition of an edge device has changed over the years a little bit. In the past, we used to talk about IoT. So I'm sure most of you guys have heard of IoT or the Internet of Things. Those are your little embedded devices, your microcontrollers, your Raspberry Pi type microprocessing devices. Those devices are now blurring with phones and edge computers and even more powerful computing hardware like server-grade hardware at the edge. Essentially, the edge is anything that's not in the cloud, but is local, close to the actual problem domain that you're trying to solve. So moving your AI to run off the cloud down to the edge has several advantages, one of them being privacy. So we live in an era where we all worry about when you type to ChatGPT and share information with it, how do you know for sure that these models are actually, how do you know these models are actually not stealing your data and using it to train, which you can be sure is probably happening in the background to fine-tune the models. Privacy, that's one concern. The other concern is data usage. So you obviously need to have a data connection. Again, the amount of data you send to a model is not a lot, but now with multimodal models where you can send image data as well and even video in the future, that'll become an issue as you're streaming data up to models. There's latency problems. And there's also, with the cloud, if the cloud service goes down or has usage problems, like too many users at once, you're stuck. So with that in mind, what I want to show you guys today and impart to you is to think and change your paradigm shift from running LLMs in the cloud to running them locally at the edge. And I will show you an example on a phone, but you don't have to use a phone. You can run it on your laptop. Has anybody here played with llama.cpp? Anybody done that? So there's been a lot of online activity around using GGML and things like it to run models locally on a PC, on a MacBook, or even a normal Windows laptop. But the idea is to go and actually run it on your phone. So without that contextual introduction, I'm going to talk today about building a GenAI app on Android using the Executorch framework with Arm KleidiAI. So that's a lot of words there. But let me start first with Executorch. So Executorch, okay, from the developers here, most of you guys are, I assume some of you have worked with AI, right? Can I see a set of hands, anybody who's worked with AI? Has anybody worked with TensorFlow? Great. Has anybody worked with TensorFlow Lite? TensorFlow Lite. So to give you a bit of history before I go into Executorch, TensorFlow is the framework that you use to develop models and train models. You work with the Keras API and you build your model using the functional sequential APIs. And then when you're done, usually a lot of people do that in a Google Colab notebook, Jupyter notebook, or you do it maybe in a different like SageMaker and Amazon. But essentially you're working usually with Python and you designing your model, you're importing data, you're doing what they call ML ops, which is basically the process of taking data, training a model, testing the model, and retraining it, and basically iteratively going through that process till you're happy with the results. But then there's the aspect of deployment of the model. Deployment is when you actually need to use the model in an application. So it's all fun to do notebooks stuff, but you can't run a notebook on an edge device. So if you're gonna deploy a model to a GPU-based system or a TPU-based system running on the edge, you don't really want to have a notebook that somebody must go into and click F5 or something. So you have to build an application. So TensorFlow Lite is the runtime for deploying models to edge devices. So Google's been working on that for the last 8 years. And one of the challenges they had was with the Android phones back in the day. You know, when you say, okay, Google, to wake up the phone, that model that ran either had to be in the cloud, or if it ran on the main GPU on the phone, it was chewing up a lot of energy. That means if your phone is in a standby state and you want to say, okay, Google, or you want to use a Google Home speaker and wake it up, you need to have a way not to have the device using too much electricity. The device has to be in a low power sleep mode, and you need a way to actually wake it up. But how do you run an AI model in a low power mode? That was the problem. So what the guys did at Google, Pete Warden and those guys, they took TensorFlow Lite and they built TensorFlow Lite Micro. So TensorFlow Lite was the runtime for running models. And when I talk about models, I'm talking about like computer vision models, MobileNet, back in the 2018s, 2010s, when those models started to come out, to run it on a phone, on an Android device. They took TensorFlow Lite and TensorFlow Lite Micro, and they optimized the models to be able to run on a CPU, and that gave rise to something called TinyML. Has anybody heard of TinyML? Never heard of TinyML? So TinyML was basically the technique of taking models, squashing them down, quantizing is the term. So we take the weights of the models and we reduce them from 32-bit precision to 8-bit precision, and we run them on a small little CPU, and that allowed Google to work with the hardware vendors to build a small chip that sat on the motherboard, and the main CPU went into sleep mode, and the separate chip was actually in a standby state, running this little model, listening for you, saying, okay, Google. As soon as you said, okay, Google, that small chip would then wake up the big CPU. That small chip uses a little bit of power, and that allowed the phone usage, battery usage to improve. Because if anybody here remembers, over the last decade, every time a new feature came out, a new phone came out, the power usage got better and better and better. We're at a point now where you still only get a day and a half, but if you look at what you have on your modern phones, you would probably got like 1 hour's battery usage out of this 8 years ago on using the technology stack at the time. So, from TensorFlow Lite, there was a whole evolution of applications called TinyML, which is basically running machine learning models not on a GPU. You guys have heard of GPUs, right? Who here has heard of GPUs? And you've heard of NVIDIA and those guys, right? So TensorFlow Lite enables you to run a model on a CPU, the main processor. And it enables you to run it on a small little microcontroller like an Arduino, and again also using the same techniques on a laptop or even a Raspberry Pi. And of course, on an Android phone. So that's where the industry moved into that space for the last 5 or 6 years. And the techniques that were developed in the TinyML space, and I mentioned something called quantization. Quantization is basically the weights in your model, you reduce their precision. So instead of having 32-bit weights, you have 8-bit weights. So you essentially round the weights to the nearest 8-bit value. So you take your range of weights of numbers in your dynamic range of your weights, and you take an 8-bit, which is 256 values you get, and you round the weights to the nearest value. And by doing that, you make the weights smaller. You effectively take away 24 bits, which is 3/4 of the size. So the model goes from fitting into whatever the model was, like a gig, it will fit in 250 megs of memory. So that technique was used to shrink a model down, and also because a chip like a CPU can more easily process 8-bit numbers, and with things like data parallelism and single instruction, multiple data, you can process chunks of 8-bit numbers together. You actually can run a model in real time on a CPU. Okay, so that was TensorFlow Lite. So TensorFlow Lite was the runtime for TensorFlow. But there's another framework that's been very popular for building ML, and that is PyTorch. So PyTorch, who here has heard of PyTorch? Okay. A lot of people probably got started on PyTorch. PyTorch was built by Facebook, now Meta, as part of their ML training framework. One thing PyTorch never really did well was work on deployments to edge. PyTorch had TorchScript, which you could use to deploy models to cloud-based services, and even to GPUs like NVIDIA and TPUs and things like that. But the whole edge running a model on a CPU wasn't really well built. So that changed about 2 years ago when PyTorch launched a new runtime called Executorch. I have a laser here. Executorch. So TensorFlow Lite has been rebranded recently to LiteRT. So LiteRT is TensorFlow Lite. So you'll see they both got logos, look similar, and they do similar things. So if you come from a TensorFlow world, you can run your model in TensorFlow Lite on the edge. If you come from a PyTorch world, you can now use Executorch. There's also interoperability, so you can take models built in one framework. With a bit of work, you can move them to the other. So my talk today is going to focus, I come from a background working a lot with TensorFlow Lite and TensorFlow. I'm going to talk about Executorch. And the reason why I'll talk about Executorch is because I'm talking about a model called Llama. Have you guys heard of Llama? It's an open source model. So Executorch, the features Executorch provide are, as I mentioned there, portability. So like TensorFlow Lite, or LiteRT as it's called now, you can easily move models between different edge devices. You can run a model on a phone, you can run it on a Raspberry Pi, you can run it on a laptop, you can run it you could even run it in the cloud if you want to as well. So you use the same workflow and you can export your models across a range of target platforms. And what Executorch does is it actually optimizes the model for you for the target platform. So there's the tool chain, the tooling is quite smart. It actually can identify what you want to export to, and based on that, it inserts the correct optimizations for the correct platform. Again, that gives you a productivity boost, because in the past, if you had to target a CPU or GPU or TPU, you'd have to make custom changes to your deployment pipeline to target the types of operations that the CPU can support and things like that. Now you have a seamless tool chain that can just do it for you. So it provides a level of abstraction that makes life easy for you as a developer. And in this day and age, we're going into the world of agentic AI, and we all want to be able to easily, quickly work on our final product. We don't want to be sitting with tooling, stuck, scratching our heads, things like that. So, and then of course, performance is the main point here. Because of optimizations, which I'll touch on now in the next few slides, you're able to actually squeeze out the most performance for the type of platform you want to deploy to. So there will always be cases where you need to deploy a very complicated model to a GPU. And that would be like maybe if you're running a segmentation model for vision, self-driving car thing. And again, if you're running a agentic system where you have a lot of clients connecting to it. But that makes sense in the cloud environment where you have lots of clients connected to the cloud. What I'm talking about now is if you bring the model to the edge, you reduce the number of connections to the model. So you don't need to have a GPU. So remember, when you're running that model, ChatGPT, you are sharing it with thousands of users, millions of users actually across the world, and millions of apps that are built on APIs talking to it. When you run a model locally on your own device, it's only you and your agents that are going to make use of that model. So you have a lot more control, so you don't need a GPU. You can run it locally on a CPU, and you can actually, that way, benefit from local processing versus cloud. And again, key thing in mind is the paradigm shift for building on the edge is you are the client to your own model. You and your agents, that's it. There's not a million people hitting that model, it's just you define 10, 15 agents, one client, the app running locally on the device. So that's why it's now possible to actually use CPUs to run AI models on the edge. So I hope that makes sense to you guys. It's a very important distinction. You take control of the whole ecosystem now, essentially. So, the Executorch has a workflow. So you'll see, you start with a PyTorch program. So they call it eager mode, like when you build like in TensorFlow to you in notebooks. You can build a program, you can run it, test it, you can build a model, you can experiment with different data sets, ML ops basically. But once you are done, they refer to it almost like a 3-step process. What you do is you export the model to a PyTorch graph. So has anybody here ever worked where you export a model and you actually can see all the steps in the model, how it executes? Netron, if you ever use Netron, anybody ever use Netron? So a machine learning model, this is something which you guys must remember. Any model, right? Whether it be an LLM, whether it be a vision model, whether it be an audio processing model, essentially what that model is a learned set of weights that are basically put into a graph, execution graph of operations that operate in sequence with each other and sometimes in parallel, but it's essentially a graph of operations that execute. And all models can be decomposed. There's a tool called Netron where you can export a ONNX file or a TF Lite for TensorFlow Lite or Lite RT, and you can actually see all the operations of the model that execute. And each one of those operations are implemented usually in a piece of code called a kernel, and that's usually implemented on a GPU. So if you're using GPUs, use CUDA, or if you're using CPUs, you have custom, it just uses basically the CPU to implement. For example, one of the most common operations is convolution, which is a mathematical operation, and matrix multiplication. So that's usually a function that will be implemented in different ways across different pieces of hardware. If it's on a GPU, people make use of, for example, CUDA or OpenCL, and what they will do is that will then take the matrix multiplication operation and translate it into a sequence of instructions that the hardware can do better. So a GPU has lots of little cores that work with small bits of memory and lots of data. So we'll split the operation up into parallel operations and put the results together. If you're running it on a CPU, it will do it in a manual way. It will take the data and do the matrix math the way the operation is defined in a math textbook. And that's usually slower in the past. Arm has of course made changes to the CPU architecture and has included things like vectorized instructions. What vectorized instructions are, you can do an addition on an array. You can take two arrays and add them together in the past, or multiply them together. In the past, you'd have to do element by element. You can now do groups of elements at a time. They call it single instruction, multiple data. That means in one instruction cycle, you can multiply up to a dozen numbers together. So you actually run through your array much faster. So you're starting to get GPU-like features in a CPU. And that SIMD, or single instruction, multiple data operations, really accelerate and improve the performance of matrix multiplication, which is one of the core operators in the execution graph of any model. Matrix matmul, they call it. And usually you have these things called multiply accumulates in GPUs. Your CPU can now start to execute your models a lot faster. That's where I'm heading to. So when you export your graph, if you look at the bottom of that block exported graph, you see a directed graph diagram. And anybody who's seen these, you've seen them before in textbooks. It's essentially, that's directed graph. The arrows are flowing in one direction. And it's basically saying this operation happens, and the data gets passed to two separate operations that occur, and then another two, and then the result gets passed to another. Each one of those are like functions that are running inside the model. When you take that exported graph, you then compile it to an Executorch program. So what Executorch then does is, depending on the target that you want to deploy to, it then says, okay, I'm deploying this to a TPU on Google. It then goes and actually finds the library that implements those nodes of the graph or the operations on a TPU. Or if you're running on a CPU, it will then take what's known as XNNPACK, which I'll explain just now. But it will then build a program in Executorch ops. And I'm getting into a bit of technical detail here, but it builds an Executorch intermediate format. And then when you're ready to run your program, your model you can think of as like a function. Think of your machine learning model as just a function, a black box. You give it input, it gives you output. If it's a computer vision model, you give it a picture in a two-dimensional array, and it gives out either classes, or it gives out coordinates of where people are, objects are in a picture. Or if it's a LLM, you give it a prompt, and the result is the response to the prompt. But at the end of the day, you can think of any model as just a black box. What Executorch then does is, depending on the device you load the model onto, it then supports ops, which are the operations that are, these are all operations in the graph. It supports a default set of ops for CPU, but it also supports targeting specific types of hardware like TPU, GPU, and Executorch uses something called delegates. So let's say you build your own type of chip. You come up with your own chip, and you want to support Executorch. You can then use a delegate. You can build your own delegate that you plug into Executorch, and that will then optimize Executorch. It'll give Executorch the formula for how to run, or the code for how to run that particular operation on your own chip more efficiently. So for example, if you want to add two numbers together, that would essentially be an add instruction. So if you're using assembly language, it'll be add and then two registers, and the result, if you're using C or Python, it'll usually be a call like C equals A plus B. Now what happens is, behind the scenes, if you're just using a normal CPU, the op will then just use the add instruction in assembly. But let's say you've invented a new chip that you've got a special instruction that you want to add, and it runs much faster than a normal instruction. You will then create a delegate, and you'll write the machine code or assembly code for that instruction into the delegate, and Executorch will say, okay, for this chip, I'm not going to use the default op, I'm going to use the optimized op. That makes sense. So that's what Arm has done. Arm has built for the CPU optimized bits of machine code that can plug in as a delegate into Executorch to allow the model to run faster on an Arm CPU. So I know it's a lot of technical stuff, but we just go. And then the inference is the process of running the model at the edge. So inference is when you call the model and when you actually provide an input to it and get a result. Just click next slide. Can you guys change to the next slide? Thanks. Okay, cool. So Executorch, XNNPACK. So again, like I mentioned, you got GPUs. You also got NPUs, which are neural processing units. Those are like mini GPUs on small devices, but those devices are not consistent. There's many different versions and many different brands. So some perform better than others. So my focus here is CPU, because you can get a lot of performance out of a CPU versus using other accelerators. So XNNPACK is the back end, the generic back end for CPUs in Executorch. So whether it be AMD, Intel, ARM, whatever, XNNPACK supports default CPU operations. So what Arm has done is Arm has taken XNNPACK and they've created a delegate for XNNPACK where they've plugged in optimized routines for the ARM CPUs. And those optimized routines are called Kleidi. So XNNPACK, you'll see it says introduces highly optimized implementations. So the guys at PyTorch have obviously worked with many hardware vendors to try and optimize for different CPUs. And Arm has got a partnership as well to support Kleidi and obviously integration. So Kleidi comes for free in the Executorch framework. What I'm showing you today, if you use Executorch, you pretty much don't have to even think about it. It's there in the background for you. If you're targeting an ARM-based device, like I'm showing a Samsung phone here, it automatically, when you build, it will automatically bring in, if you choose the workflow for XNNPACK, and say you're targeting an ARM-based device like a phone, like a Google Pixel or a Samsung Galaxy S24 or 22 or 21 even, it will automatically do this for you. So what I'm showing you today, I'm talking a lot of technical stuff, but it comes for free if you use Executorch in the background. So I'm just giving you some information of what's going on in the background at a high level, so you can know that it's not just click, build, there's actually some stuff happening. There's a impact to the performance that you can actually see. So, and again, so we move on to the next slide. Arm KleidiAI, or Arm Kleidi, is a set of software libraries that Arm has built recently, launched this year. And while Arm is a chip design company that focuses on CPU architecture, and also mobile GPUs, Mali GPUs, for gaming, mobile gaming, Arm also is a software company. So in the sense that Arm has been heavily focused on building out software to support the hardware. And we also have a developer program, which my colleague will talk about just now. But the whole point of that is you can't have hardware and software and not have an ecosystem around it. So what we're doing here is to engage with you and try and equip you and give you free resources to help enable you to build new applications. So Kleidi consists of two sub-projects. One is KleidiAI, and essentially what KleidiAI is just the operators for matrix multiplication that have been handwritten in assembler language and tuned and put into Executorch as a delegate in XNNPACK. So it comes there in the background. So when you choose an ARM CPU and you're running AI, and you're using Executorch, it automatically will pull in the Kleidi libraries and compile it into the actual program for you, the final model for you. And the beauty of Kleidi is it's evolving, but right now it supports the key operations of matrix multiplication, and it leverages the CPU features in ARM, the SIMD, what I spoke about, the single instruction, multiple data, what they call vectorization as well in the newer CPUs. It leverages that to give you a performance boost over other CPU architectures. So now suddenly when you're running your AI model, besides the fact that you're squashing it down, quantizing it, all that stuff, the CPU itself will give you a little bit more of a it's like running a supercar versus a normal car. So, and Kleidi CV is a whole different set of libraries. Has anybody here ever used or heard of or worked with OpenCV? Right. So OpenCV is a set of computer vision libraries that allow you to do things like change sizes of image, detect edges. It's more of a pre-AI type of way of doing analysis of graphical data. It's from the field of computer vision, like I said, it goes back before deep learning, and it uses some internal machine learning, classical machine learning techniques. So you can do face detection, you can do a lot of things. A lot of the times, people don't really use can you go back a slide? A lot of the times people don't actually use the facial recognition detection anymore inside OpenCV, but they still use OpenCV for things like scaling images, copying images, changing the color, like space of the image. And so what Arm has done is Arm has created KleidiCV, which like KleidiAI for the matrix multiplication, are a set of optimized routines that plug into OpenCV and accelerate the computer vision classical operations, which usually happen before your image gets to your model. These transformations you've got to do in your image, like rotations and stuff, and that also accelerates that. So if you ever used OpenCV, you're most likely using it on your normal CPU, and you'll see it doesn't always run as fast as you want. You can run on a GPU, but you don't always have a GPU available. KleidiCV will allow you to run OpenCV models on a ARM CPU faster, OpenCV code faster than you would be able to run it on a normal CPU. But I'm not talking about that today. That's just something I'll mention. Also, Kleidi is also integrated into Google Media Pipe. Does anybody use Google Media Pipe? So if you use Media Pipe, if you don't want to use Executorch, you can use Media Pipe. And there's a lot of functionality available in Media Pipe to build various computer vision applications. And what you can do is you can essentially use that for free again. It's built into Google Media Pipe. The cloud acceleration kicks in automatically if you're running something on your ARM-based Android device. So yeah, I discussed earlier the Executorch delegate. So essentially it's just showing that the KleidiAI plugs in as a delegate into XNNPACK for Executorch to allow you to happen. But again, this is all happening behind the scenes. Can you guys go next slide? Okay, cool. So yeah, so you can see, just go back a slide. I'm not going to switch on the laptop yet. I'm just preparing. Okay. So, Kleidi accelerates your model performance by up to 190% for Llama 3, and I think the Microsoft file thing. Just put this on quickly. So I'm going to try and show you a demo quickly, but before I do that, let me just see why this is not working. Okay. In the meantime, I'll continue talking. So yeah, so that's the upliftment you get on your model performance. There we go. That's the upliftment you get in your model performance by using Kleidi. So in other words, if you just use normal Executorch, XNNPACK, even on an ARM CPU or any CPU, you'll get a certain level of performance. If you use Kleidi, you get 190% boost. That's quite a lot. And you'll see it in action shortly. So, there is a... okay, just minimize that. Okay, just go back to the slide deck. I'll tell you when I want the slide deck on. When I want the laptop on. Thanks. Okay, just move to the next slide. Okay, that's not the, why is it showing the laptop? Okay, something's wrong here because it's showing the laptop. It's supposed to show the next slide on the deck. There we go. So Gemma 2 is obviously Google's small language model. You can also run it with Kleidi and Executorch as well. I encourage you guys to look into Gemma 2. I'm going to show Llama 3.1, 3.2, but look at Gemma. They both do similar things, and data advocacy for data privacy and best practices. Take a look into the philosophy behind Gemma 2 and small language models. So we're moving into the era of SLMs. If you walk away with one thing from this presentation, walk away with the acronym SLM. Not LLM, not large language model, SLM. An LLM is designed to run on a big backend on the cloud. A SLM is a small model that can run locally, and you can embed it in your application for different tasks. Again, we get a 25% improvement on Gemma as well. Okay, next slide, please. Okay, next slide. I don't know what's going on there. Okay, cool. So now I'm going to show you guys quickly a demo of running, let's see, get it started, running a Llama 3.2 app. So, okay, just before you switch over. Okay, so here I've got Android Studio open, right? And I'm running this app on my phone. So, yeah, chat history. So, let me just quickly close the app. So first thing I'm going to do is, I'm putting my phone, okay, my phone is fine. I'm running the app. Okay, what's going on? The app is, I'm just building the app quickly and running it because the app's there. You just clear this history. So there's the app. You can see it's not very clear on the screen, but what the app is showing you, there's an input prompt here, and there's a response prompt. It looks like WhatsApp, and then there's a settings button and a logs and the amount of memory being utilized. So this is an S24 Ultra phone. So this phone's got 12 gigs of RAM. So that's one of the issues when you run small language models. You still need to have a phone now that's got a lot of memory, but models like Gemma 2 and the Llama 3.2 can be quantized down to about a gig. So you can start to run them on smaller phones as well. So I'll show you quickly. I've got 9 minutes left. So I load the model. I'm selecting, okay, so this model is copied to my local phone. You couldn't quite see it there, but it's a PTE model, a PyTorch executable model. It's been exported to PyTorch runtime. This app has got it's an Android, built-in Android studio using Kotlin, and the actual Llama model runtime with KleidiAI and XNNPACK is actually built with a Java native development kit, because the code that runs the model is actually written in C++ for optimization as well, and KleidiAI is a C++ library. So but Arm provides, or PyTorch provides if you follow the documentation, a library, an AAR file that you can bring into the project that contains a API that you can use to access the models for you. So it's all in this app, documented there as well. But I'm also selecting a tokenizer. The tokenizer contains the mappings to the actual text. And I'm saying load model. Boom. Model's loaded. Now I'm going to say hi. Here's the model response. Unfortunately, you can't really see so nicely, but it's saying here, how can I help you today? Let me see if I can make this bigger. Okay, that's better, yes. Now what I'm going to do is, I'm putting my phone into airplane mode. So my phone is now in airplane mode, right? I'm not connected to the internet. So I'm saying how are you today? I'm saying I'm at a conference. Let me see, okay? So let me just zoom out so you can see the response. It's saying to me, how is the conference going so far? I'm going to say, good. You see how fast it responded? Now, what I want you guys to realize here is, this is not running on the cloud. This Llama is running locally on my cell phone. It's not using a GPU, not using a TPU, it's not using an NPU. It's using the good old CPU, the Arm CPU. The Cortex X2 CPU inside X1 CPU inside here, and Cortex A. I'm sure you can agree that response is probably faster than the response you get sometimes from ChatGPT, right? I'm sure you can agree, because I'm going to ask it, write me hello world in C. They generated a piece of source code for me. Now, this is happening locally on my device, and it's doing it at a rate of 43 tokens a second. Now, I know if I go to ChatGPT and ask the same question, it'll probably respond as fast or maybe a little bit slower depending on connectivity. Now, this is a paradigm shift for you guys. I want you to think about this. What can you do with this? There's a lot that you can do with this. I'm putting my phone off. So, guys, I'm just going to disconnect the phone. So, there's a lot that you can actually do with this technology. And I want you to think about how you can apply this in your own applications. One of the early applications that is being used for is summarization. So you could take documents, have them or information locally on your phone, like if you're running an agentic app, and you could then summarize it locally using the LLM. Because it's a small language model, it doesn't contain all the knowledge you'll find in the massive Llama 450 billion parameter, because obviously it's going to take up too much. Your phone doesn't have 100 gigs of RAM. But it's LLM technology. The LLMs, they learn context and how to understand data. So one of the things they learn is they learn to store lots of information within the weights. But they also learn to understand context and semantics of data. So this model, what you're going to use it for is not so much to query like Wikipedia and say, tell me what happened in 1942 in this country. That's where all the big models store lots of weights to contain data. you're going to use the AI technology, you're going to use the LLM's ability to reason and do logic and understand data to take data running on your local apps and contextualize it. So, for example, if you're building a healthcare app, you can use that to summarize incoming information that somebody Googles and actually give them the results in a more summarized form. You can also use this, you can think of this like a child's brain, because it doesn't have all the knowledge that a large LLM has in terms of memory of historical data, like facts, but it's got the ability to do reasoning and logic. So this is like a 10-year-old kid that hasn't finished school, which you can then put it inside your app and actually use the logical human brain type thinking of LLM to actually understand things. I'm sure you guys can see this is a whole new way of doing things. Now everybody's talking still about cloud and that. This is the future. The future is agentic AI at the edge, LLMs becoming SLMs, small language models, and it's going to be so it's going to actually be going to be something. Another thing I want to show, if you could just switch back to my laptop quickly, before I hand over the last 3 minutes to my colleague. If you don't have an Android phone, my internet seems a bit slow here. Okay, if you don't have an Android phone, specifically one that's got like 12 gigs of memory, Arm provides a service called Arm Virtual Hardware. So it allows you to run a simulated phone in the cloud. This is something really cool for developers. I just wish my internet wasn't so slow. Derek, you have faster internet. This app is available. The source code for this whole app is available in the Executorch repo. So all the code is there, and you can download the app, and you can play with it, and you can actually modify the app. It's an Android Studio app. It's in the Executorch repo under examples, Llama demo. The source code is that you can take this app and you can use it as a starter app to build your next big $1 million product. And one of the cool things I think we can do with this is language translation, because an LLM can be, you can also fine tune the model yourself, the SLM, and then run it locally on your phone. So a good example would be a translation for one of the, I understand like locally here there's many languages. You could fine tune a model that you must figure out on your own, do ragging to bring documentation in and build and then deploy it locally without connectivity on your phone. Arm Virtual Hardware, okay, here we go. Arm Virtual Hardware is a product that's available. There's a free tier you can use for a short period. You get like, I think you get like a limit of 1 month to use it, and it allows you to run. I know I'm almost up with time, but I just want to show this is very important. It allows you to run an Android device. Choose a product. You can choose a generic Android device. Select, create device, and you can run a device completely in the cloud, ARM-based Android device. And booting up now, and you can use this for testing your code. And so if you ever use Android Studio, sometimes the emulator is very slow. If you don't have a proper PC or you don't have acceleration, you can use this to run. It's called ARM Virtual Hardware. So you get a free tier, which you can use. Also, you also get you also can run a Raspberry Pi here as well. So for those of you interested in playing with Raspberry Pis, you can run a virtual Raspberry Pi 4. Was here. Yeah, a virtual Raspberry Pi 4. You can boot it up, and you'll see the Pi will boot up on the right. So it allows you to experiment with running LLMs and AI on the edge and any IoT projects. But I just thought I'd share it with you guys. It's called ARM Virtual Hardware. So yeah, I know we're almost out of time. Can I just give Derek 5 minutes to explain the ARM developer program? So can you quickly switch back to the PowerPoint? Got 2 more slides. Can I just switch to the next slide? Okay, just switch forward, it's fine. Just go to the last 2 slides. I'm going to skip over all of that. This was the steps up, but we never had time to go through the steps of how to do all of this, to build the app. But I encourage you guys to go to, before you move on, just go forward, go forward. Forward. Are you going backwards? Go forward. Go forward. The PyTorch repo, go forward. This presentation, I assume, will be available, I'm sure, with that's the app. Okay, yes. So I'll invite Derek quickly to the stage, and he'll tell you about this. You can access learning paths to actually learn how to do all the stuff.
Hello, everyone. Yes, so my name is Derek, and I'm an ARM ambassador. So the ARM developer program was launched 2 years ago, and what the ARM developer program seeks to do is to bring anyone that is developing on ARM. So like Peter said, ARM is into mobile phones, Windows. There's Windows on ARM, there's cloud, there's server, there's embedded system, there's microcontroller. So whatever you are building, you might not know, but you are building on ARM. So with the ARM developer program, you get access to free tools like resources, learning path, and then once you sign up, you get access to our Discord channel. There you get to meet ARM ambassadors, you get to meet ARM experts. So in this conference, we have 4 ARM ambassadors here. So there's Marvin and Gessa, there's Robert John, there's Peter, and there's myself. And you get to have access to ARM experts. ARM experts are ARM engineers that work with ARM. You get it. So you can visit our stand. There's a QR code for you to scan and join the developer program. If you come early, you might have access to some ARM swag. We have swag that, how many of you have gotten some ARM swag already? Okay, good. So if you don't have any ARM swag, you might have to pass by our booth and then get some ARM swag for free. Also, once you sign up to the developer program, you can get access to developer meetups where you get to learn and connect with other developers. So that is all we have to tell you about the ARM developer program. If you have any question, you can ask and then we'll gladly answer. So you can come to our booth and then you can access any question and we'll gladly answer. Thank you so much.
Thank you.